All right, so let's begin. Do you guys remember anatomy and physiology from the summer? I'm trying to forget. It depends. I need to focus on my head to toe, man. Shut up. All right, so I am going based off of your IOs that are involved in structure and function. So any IOs that you see in the neuro unit that are, say, structure and function of whatever, that's what we're going over. And I don't know if this list covers everything. This was given to me, and they said, cover this. I said, okay. So a lot of this is going to be interactive. In other words, since it's a review, you guys should be able to tell me some things. For example, what is that a picture of? The brain, sweet. And this is an MRI. Anybody know what kind of section we call that? Sagittal, good. So this would be a sagittal section of the brain. We're looking at it from the midline as if you were looking, like split the hemispheres in half, and you're looking at the through the longitudinal fissure. Okay? So there are certain structures that you should be able to recognize in there, and we'll go through, like I'll point them out and I'll say, what's this? But there are certain structures you can't see because we're looking at the midline. So there's some pictures in the next few slides that will cover that material as well. So when looking at this, what hemisphere are we viewing? Left or right? The right hemisphere. And this would be what of the brain? What part of the brain? Frontal or anterior. And this would be posterior, just so we get an orientation to where we are. All right, so we know what hemisphere we're looking at. What lobe would this be? Frontal. Parietal. Occipital. What lobe can't we see? Temporal. And it's an obscure one. What'd you say?
Not the right word. I said apices.
No. Insular layer. There's the insular lobe as well. All right, so those are the various lobes. We'll go over what they do eventually. Okay. What are all of these bumps called? Gyri. Those would be gyri. Those are the bumps. And therefore, all of these black spaces that are going between those would be sulci. All right? And there are certain sulci that you should be able to identify, which we'll cover in the next slide. But going back to summer, what is the most important sulcus you need to know? Central. Because that divides what? Not hemispheres. It does not divide hemispheres. Say it. What? Oh. Motor and sensory. Right? Okay. It's a good thing we're doing a review. All right. All of this stuff right here that we see in a very thin layer at the periphery, what do we call that? I heard it. Gray matter, all right? What is in gray matter? What is it made of? Obviously neurons, but what part of neurons? Pardon? No.
Soma.
Pardon?
The soma.
Soma, cell body, and what are the connector pieces? Dendrites. So that's where all your connections are going to be made. This is where all the processing occurs. And then all of this stuff underneath it that goes down is the what? White matter, which are the axons. Good. And why is it white? What makes white matter white? What makes axons white? The myelin sheath, which is made up of fat. Okay, so fat. Because we have to think of it as an electric unit, we have to have cords going up and plugging in to the gray matter. So that's what the white matter does. And that's why it's on the inside of the brain. Where's the white matter in the spinal cord? Outside, right? It's on the outside. And gray matter's on the inside. All right. And then what's this lovely thing back here? Cerebellum, which means little brain. Okay. There are a bunch of words. I'm going to point to a structure, and you tell me which one of these words it belongs to. What is this? Pons, good. What is this? No. No. It's the T1 who said it. Thalamus. Good. So there's your thalamus. And then this would be your midbrain. And what you see here is your superior colliculus, inferior colliculus at the back, right? That means if this is your midbrain and these are the superior and inferior colliculi, well, what's this little structure right here? Sweet. Pineal gland. All right. If this is a thalamus, what's this structure here? That would be your hypothalamus. And then that would mean hanging off here would be your pituitary gland. Good. Hypothalamus. All right. And we showed midbrain. Awesome. And then what would this be? Medulla oblongata. This, not on here, but it would be the spinal cord. So it's exiting. All right. And then what is this structure right here? Corpus callosum. That leaves one thing left over, which I don't know if we covered or not in the summer, but it is something that's on your IO list to identify. Septum pellucidum. What does septum mean? Wall, division, something like that. So it's a division between the ventricles. You'll find it right here. All right, there's literally a membrane made up of neurons, some neurons and some connective tissue, amongst a few other things, that separates the lateral ventricles. Okay, so that's a septum pellucidum. All right, yay, you guys knew it. Most of it. You got in trouble with the thalamus. All right, easy way to remember that. Remember, the thalamus is always a roundish structure, and it's always going to be directly under the corpus callosum. So you're going to find it next to the septum pellucidum and the corpus callosum. All right, that's an easy way to remember it. Thalamus. Let's see. Thalamus, midbrain, TMPM. I don't have a good thing for that. TMPM. All right. You guys come up with your own. You guys came up with some great ones this summer that were kind of raunchy, but they worked. They worked. All right, good. You will be in practice. You guys may see patients with neurological disorders. Are you ever going to be able to take off their skull and look at that? No. So you have to get used to looking at these images, because these aren't going to be available, right? You can't see this. This covers the rest of the stuff. Major sulci, central sulcus. How would you... Well, it's fucking right there. All right. Right in the middle, which separates the frontal lobe from the parietal lobe, and also... One and two. Which one's motor? Which one's sensory? Motor, sensory. All right. Remember, motor is always part of the frontal lobe. Sensory is always behind it. I guess One way to remember that, you do it, then you feel it. Okay? You do it, then you feel it. Oh, God. Yeah. All right. Where's our lateral sulcus then? Would be right here. And that would separate your temporal lobe from parietal and frontal. And then your parietal occipital lobe. This is a shitty drawing right here, but kind of right there. There's a sulcus that you can see that literally separates those two. See if I can find it in this. That would actually be right here. So you can see it in an image. All right. And just to round things out, that would be your longitudinal fissure, and that's the one that separates hemispheres, not the central sulcus. So central sulcus works front to back. Longitudinal fissure, left and right. Okay, and then this is briefly a slide on your insular lobe. If you peel back the temporal lobe, it's this little piece of cortex right here. All right, and it is connected to the limbic system. It's also connected to the lobes that it is in between, and these are just a summary of its functions. Okay, basic functions. There's a less known about the insular cortex than there are about the other lobes, but those this isn't one of your IOs. I put it there just in case you wanted to know what it does. So I'm not going to cover it. It's information's there. All right. Let's go into an axial image of your brain. All right, axial would be going from top to the bottom. All right, if you're interested, I pulled these pictures. They won't let you copy and paste, so I had to do screenshots of all of these. But you can find it at this site that's here, and you can literally scroll through all of the images. I only pulled a few key ones to get the images across that I wanted to show you. So everything that's in green is part of your IO list, and so those are the ones I wanted to highlight. So these high contrast areas right here, that would be part of your left and right or lateral ventricles. All right. Here would be the frontal horn, also known as the anterior horn or ventral horn, and this would be the occipital horn or posterior horn or dorsal horn. Right? All of those you'll find depending on what book you look at. You also find clinically things are called different than what we call them in science. Right? So I think I told you guys that this summer. Be familiar with multiple levels of terminology. All right? So those are your ventricles. Right? There's fluid in there. It's probably glowing that way. I don't know a whole lot about imaging because they put a contrast dye in there. Okay? And then the rest is black, representing the soft tissue. So between those, you can actually see it pretty clearly. The septum pellucidum, it's just a dark area between the ventricles, showing you that there is actually a piece of tissue there. Right? I'm not just making shit up. All right. So associated with these ventricles, what I hope you guys do, and this is what I try to do when I'm putting this together and getting an image in my brain of what I want things to look like, kind of put these pictures together with the sagittal pictures and try to get an idea of where these things are in relation to each other. All right. So one thing that may not be clear, all this stuff right around out here, that's part of your basal nuclei. Remember the basal nuclei. That's what goes wrong when we have Parkinson's disease. So the caudate nucleus right here is part of your basal nuclei. What else did I miss? Oh, and then back here we see the falx cerebri. Do you guys remember what that is? No. It's a membrane. What do we call that membrane? That hard, tough membrane that surrounds the brain. The dura mater. So this is the dura mater that separates the hemispheres. Right? It goes right between the hemispheres, and you can actually see it on the image here. All right. So other parts, you still see the caudate nucleus here. It's extended a little bit because we're going down. Top of the brain. Next level down. We're moving down the brain. Okay, so starting at the top, moving down. Caudate nucleus. Here's our putamen. All right, on either side. Again, part of your basal nuclei. And then here, we see the thalamus. All right, so now we get a little bit better of a picture. Your thalamus is right on either side of that septum pellucidum. And then outside of that is where we'll see our basal nuclei. All right, all of these are subcortical structures. What does that mean? When somebody says subcortical, it's below the cortex. Right, the cortex are all our lobes: frontal, parietal, occipital, temporal. This is below the level of that, which tells you that they're involved in lower brain functions. Okay. Oh, forgot. Internal capsule. That's these lines right here. All right. The internal capsule is basically a dividing line between parts of the basal nuclei. Why can't I? I'm going to write it down. Basal nuclei, just so I don't forget it. All right. So they separate your caudate nucleus from the rest. Okay. You also have an external capsule, which we're not going to cover because it wasn't in your fucking list. But internal capsule, this would be the external capsule here. Going down, anytime you see white, you're going to suggest that it's what? Part of your ventricular system in the brain. All right. So we see this interventricular foramen of Monroe. All right. So that's the hole between the ventricles that allows flow of cerebral spinal fluid, and we'll go into the flow a little bit later on. And just behind that, that's the approximate location of the pineal gland. What haven't we seen yet in the brain? That would be up here in the anterior region. What haven't we seen yet? Eyes. So all of this is still above the level of the eyes, just to give you kind of an idea of where we are in the brain. So this is still above the level of the eyes, probably about right here. Okay? And then here we see another part of the basal nuclei, the globus pallidus. All right, and again, I'm just trying to get you to think 3D. I don't care that you remember all this right now. I just want you to try to put this picture together. Now, remember, the lateral ventricles come together. You have the interventricular foramen of Monroe, which is back in this area. But then you have the third ventricle right here, which is right just anterior to where the thalamus would be. Okay, and remember, the third ventricle goes down to the cerebral aqueduct and then to the fourth ventricle. Here we see the tentorium cerebelli. What are those?
The fissure between the cerebellum.
Not the fissure. It would be the dura mater between the cerebrum and the cerebellum. All right. So right at the spot where you're starting to see the tentorium cerebelli, so the just above the cerebellum, now you start seeing eyes. All right. Are these the eyes, though? No. They are the muscles for the eyes, the superior rectus muscles. All right. So that's where we're located, just to give you a point in space. Now we see the eyeballs. So these are all the structures located at the level of the superior portion of the eyeballs. And the only thing I want to point out here is our cerebral aqueduct of Sylvius. All right. I was in the shower, and I was thinking about this whole concept of naming things after ourselves. And I was like, you know what? I don't like it. And I'm not mad at the people who named it after themselves because they weren't always named after themselves. It might have been a committee that named them after in honor of that person. They named them after themselves because they didn't have any idea what the fuck these things did. So they're like, well, we'll just call it the Aqueduct of Sylvius. Later, we found out that it's the cerebral aqueduct, and we know what it does. So we, as more modern people, should change these and use those changes. We don't. So we're the idiots, not them. I'm off my soapbox. All right, so now we're right dead center in the middle of the eyes. We start seeing the temporal horn of the lateral ventricles, because remember the lateral ventricles had the anterior horns, posterior horns, and then they had those side horns. We'll see in a couple pictures later. So we start seeing the temporal horns of the lateral ventricles. And then finally, I forgot one thing. We also see the very top now of the cerebellum. How do we know it's the cerebellum? Remember, the cerebellum has a slightly different structure than the cerebrum, and it had these really tightly folded areas called, you guys remember? Folia. Folia. So now that you start to see a folia, like, oh, okay, now we're in the cerebellum, top of cerebellum's right in the middle of the eyes, so now we have an idea of where things are in relation to each other, still. And again, fourth ventricle. So fourth ventricle we know is right in the dead center of the cerebellum. So we see the vermis of the cerebellum, and then the two lobes right here. And that's it. Okay? So those are the structures we wanted to cover. And the goal of that is to kind of give you, if you're looking at these images, there are landmarks you should be able to recognize so you know where you are. Okay? That's the point. What I hope is when you guys are covering the Clin Med part of this, you're like, oh yeah, I know where that is. I get it. All right, I don't think I need this anymore. I'm going to completely screw it up. All right. So, continuing to look at the cerebral structure, these are from the Anatomage app, not the Anatomage table. That's why they look a little shittier than the Anatomage app. But I think that the limbic system, which is what this is part of, is one of the more difficult things to visualize in your head. Like, where the hell is this thing? We know it's subcortical, and we know it surrounds the ventricles, but where are these things in relation to each other? So this is just to show you, again, where these things are. In the next couple slides, we'll cover what the different parts are. So they don't stick out very far. They're under the structure of the frontal lobe there. So, and they only go out about as far as that light blue is the ventricle. So they only go out as far as the ventricle does and lie just underneath it. All right, so what is the structure involved in memory? All right, if you guys had to pick one structure, say, I know that one for sure is involved in memory, which one would you say? Hippocampus. Hippocampus is your biggest one. All right, so the hippocampus involved in spatial memory, where things are in relation to each other, as well as explicit or declarative memory. What that means is memorization of facts. Okay, general knowledge. Also involved in memory consolidation. Do you guys remember what that means? Memory consolidation is the conversion of short-term to long-term memory. So that's what the hippocampus does. That's how it's involved in memory. Where things are, what are they, and how can we put that in this proper space in our cerebral cortex. The amygdala. So the hippocampus, it's color-coded. This is the hippocampus, this yellow stuff right here. I always made fun of those people in college the first time I went. That highlighted everything different colors, and I know you guys do it. And it's so beneficial. Like, I realize that, like, anyway. So these are all color-coded. Anytime you see purple or yellow, it's corresponding to the part in the brain. The amygdala, that is this little structure right here. Right here. It's not this. It's the little structure right here. All right, the amygdala, that is associated with fear and aggression. All right, fear and aggression. Facial evaluation, so I look at Kelsey and I recognize it as Kelsey. Right? If there's something wrong with the amygdala, I'd look at her and I'd be like, I don't know who that is. Social processing. In other words, do you miss social cues? Do you not pick up on them? If a girl's indicating that they like you, do you... Like, my amygdala is all fucked up. I know that. Also involved in odor processing. And this is really interesting because the fact that it's involved in odor processing and fear, you ever heard that term, smell the fear? It's a real thing. All right? And they also say, okay, so these are all memory structures. The amygdala is also involved in memory. So, smell is one of the biggest triggers of memory. You've probably heard that before. And that's because the amygdala, which is involved in smell, is directly connected to memory circuits. Okay? Cerebellum, of course, that's way back here. That's involved in your muscle memory. So you practice your golf swing and you finally get it right. Your muscles know what to do. That's all back here. It's not a conscious thing. That's why they say stop thinking about it and just let your muscle memory do it. Right? Because what goes on in the cerebellum, not conscious. And then the prefrontal cortex. Where's that? Central sulcus, about. Frontal cortex, prefrontal cortex. So the very front of your brain. Okay? That's involved in memory encoding and retrieval. So when you're studying for a test and it's going to your hippocampus and your hippocampus puts it somewhere, it's going to most likely put it in the prefrontal cortex. Right? And then when you go to take that ClinMed test and you want to retrieve that information, it comes from the prefrontal cortex. Okay? So, memory structures. Specifically, now moving to the limbic system, everything is, again, color-coded and labeled. This white part right here is the corpus callosum. When I did this, I forgot that I did it by accident, actually. This area right here, I made, transparent, somewhat transparent, so you can't see it as well. It's called the cingulate gyrus, all right? And it's a area of cortex that's just above the corpus callosum. So, part of the limbic system. All right, then we have a corpus callosum. That's not part of the limbic system, but it's a good landmark, so where you can reference where things are. This spot back here is dark green, hard to see, but that is all thalamus. And remember, that's right next to where the ventricles are, so there's your lateral ventricle. And then just outside of that, our caudate nucleus, which we know is part of the what? Basal nuclei. Look, I remembered. This thing is the putamen, and then our globus pallidus is this part right here. All right, so our basal nuclei are just on the outside of that. Still part of the limbic system. Hippocampus, that's this yellow structure down here. And the amygdala, like we said before, is this purple structure. What did we miss? Thalamus, and this other purple is the hypothalamus. mammillary body. What did I miss? Fornix. Fornix is the structure that goes from here, you don't see it, circling all the way back and comes around. All right, all of that part of our limbic system. I'll show you a picture in the next slide that kind of isolates it a little bit better. So those are all the structures involved in our limbic system, and I tried to color coordinate it so that you could see the difference between them in the anatomage that you used. So here would be a different picture of what it looks like. I don't think these show the spatial relation as well, but you can see the fornix right here coming around, part of the hippocampus, and then in the front, the amygdala. All right, so what does the limbic system do? Again, remember, this is subcortical, so underneath the cortex, connected directly to the thalamus. And do you guys remember the function of the thalamus? Relay station, right? Takes all incoming sensory information and decides where it needs to go. So it makes sense that you have these subcortical structures next to the thalamus relaying information where it needs to go. So what does the limbic system do? It's involved in emotional. This is an exact slide that you guys had this summer, so I just copied and pasted. Emotional responses. So when you guys have these primal urges to beat the shit out of something because you're mad, that's coming from the limbic system. So it controls emotional experience and the expression of emotions. Okay? Okay. They have the ability to modify the way the person acts. If you don't develop cortical structures, higher brain structures, to put the limbic system in control, you're operating strictly out of your limbic system. When you get mad and you punch through a wall, that's limbic. When you get you ever seen little kids get so excited like that's limbic. Like you don't see adults doing that. Why? Because we've learned to control it. When you see somebody crying so uncontrollably that they're in the corner in a fetal position, that's limbic system. Okay? So, again, fear, anger, pleasure, sorrow, things like that. That's all involved with the limbic system. The thought is, oh, wait, not the thought. Okay, so what it does, what it was supposed to have done, because it's a lower brain structure and we developed higher order thinking, is recognize life-threatening disruptions to a person's psychological or physical demeanor and do something about it. So, the example I like to, let's go back to the Croods. Anybody seen the Croods? You know, it's about these cavemen, and they were always under, my wife is calling me. She can, it stops recording when somebody's calling, so I was going to try to stall time, but Morgan can miss this part. They were always, the Croods, under attack from some kind of monster, right? Dinosaur or whatever weird creatures they were. And their limbic system activated and they ran away, or they got mad and they fought, or they acted crazy and started pulling their hair out and got eaten, right? That's what the limbic system is supposed to do. Now that we don't have that kind of danger, disruptions of the limbic system cause psychological problems, or what society deems as psychological problems. So its purpose is not as important as it used to be. So what it does, if you are going in the corner crying, or you're like frozen in fear, or you start running away, or you beat the shit out of the bear, it could happen. Not really. That's your fight or flight system. So it activates your sympathetic nervous system, okay, and stress responses. All right. Ventricular system. All right. This is your ventricular system. What they did to make this was they injected like a latex dye into the brain. let it go all through the ventricles, harden, then they'd strip the brain away, and what you have is a mold of the ventricles. So that's what these are. If you remember from the MRI images, anterior horn, posterior horn, lateral. Actually, no, lateral. Or not lateral. What was it? What did I say? Temporal. Temporal portion of the lateral ventricles. All right. And then from an anterior view, this is what they would look like. All around in here would be your thalamus and basal nuclei. Just to put things in perspective. And then what you see here, lateral ventricles, interventricular foramen of Monro, third ventricle, cerebral aqueduct, fourth ventricle down here. They're color-coded, lateral, third, aqueduct, fourth. Okay, just to refer back to. And also, this white thing, what do you think that is? Corpus callosum, so it sits under the corpus callosum. Just to give you a better idea of where it's located. Where does cerebral spinal fluid come from? Well, if we slice off the top of the head, can you guys believe this? I'm a horror movie fan, and I've never ever seen the movie Hellraiser. And they just came out with a new version of the Hellraiser. I don't know if you knew that. And so this weekend I'm like, all right, I had a big project to do for nursing. I put that off so I could watch Hellraiser. Sure. Don't do that, because I stressed out Sunday trying to get it done. Hellraiser. So I saw it, and that is a fucking stupid movie. I don't know how it became so popular. I guess because Pinhead looks really cool. So I watched the second one yesterday while I was putting this lecture together. Or the new one, the 2022 version, because I have Hulu. Better, but still kind of dumb. Anyway, so why I mention that? Horror. They slice people's heads off and peel skin and all that shit. So you slice somebody's head off. In the bottom of the ventricle, you see the choroid plexus. And a choroid plexus is very vascular, and that's where our cerebral spinal fluid is going to come from. That's where it's made. So what it does, and that would be located right here, it fills up the ventricles, right? Goes into the interventricular foramen of Monro, which would be right here. Fills up the third ventricle. Goes to the aqueduct of Sylvius. Okay, then it goes through this thing called the median aperture. Wait, did I say the fourth ventricle? Fourth ventricle, median aperture, and then it starts going above the brain, so between the dura mater and the pia mater, so within the subarachnoid space. It starts filling up there. Also will come from the front and do it that way, and then the rest will go down and bathe the spinal cord. All right, and come back up. All right, and then it circulates around. When it circulates up to this area in the subarachnoid space, there are these arachnoid granulations that are connected to the dural sinuses, and that's where that fluid is reabsorbed, and it gets returned back to the cardiovascular system. All of that fluid is privileged. It comes from the blood-brain barrier. Nothing gets in that the brain doesn't want in, and it takes out everything that the brain doesn't want. Okay, so it's a very privileged area. Okay, what's its function? Well, part of it's cushioning, right? If you have, there's a band I like, and they're called the Butcher Babies. Anybody ever heard of these guys? They're two girls, and they scream. They sound like men when they scream. And they're always doing the headbanging thing. Okay, when they do this, like, they can do some damage, but not as much damage as if you didn't have that cerebral spinal fluid. So your brain sloshing around in there protects it from banging up to the front of the frontal bone or the occipital bone, for example. So the brain kind of floats there. Decreases its weight because remember, you guys remember the structure of the skull? You take off the skull cap and there's like all of those sharp, bony parts. You don't want your brain sitting right on those, so it's kind of floating there, so it doesn't sit on them. All right? Your entire cranial vault, in other words, everything that's inside of your skull, holds about 1,600 milliliters of fluid if you were to fill it up. Can you imagine the research that went into that? Like, all right, let's take some skulls, turn them over, and like pour graduated cylinders into the foramen magnum and see how much goes in there. That's probably what they did. I don't know. That's it. I'm going to look that up. Anyway, it holds 1,600 milliliters. Cerebral spinal fluid is only about 150 milliliters at a time inside your brain, or inside the cranial vault. So that's about 9 to 10% of the total volume of the brain. So cerebral spinal fluid is about 9 to 10% of the total volume of cranial contents. But about 500 milliliters are formed a day. So we only hold 150 milliliters, but 500 is formed a day. What happened to the other 350? Is that our word? It was reabsorbed. Good. It was reabsorbed into those arachnoid granulations, okay, going through this path of flow. All right, the purpose of the flow is to get rid of waste, distribute brain chemicals like hormones and neurotransmitters out to the rest of the body, and stuff like that. Okay? All right. It's still recording. All right, looking at the spinal cord. Now we're starting to get into stuff we may not have covered. This is still review, but spinal cord, looking at a section of it. You guys saw the spinal cord, and it had this structure where you had looking like this butterfly that's in there. Okay, this stuff right here, GM, would mean what? Then on the outside you have white matter. Okay, opposite of what's in the brain. All right, so inside the gray matter, you guys told me, somas and dendrites. The white matter are all the cords, axons, that are going to and from the brain or to and from the limbs. So, general overview. If we look at the white matter, there are specific tracts you need to know. All right, 3 of them. Dorsal column, that would be this whole thing right here. That's the dorsal column. And remember, that's part of the dorsal column medial limniscal system, which is a sensory pathway. Anything in blue you see here is a sensory pathway going up. Remember, sensory always goes up to the brain. The other one is the anterolateral system. So this would be anterolateral, front and side. All right, the other part of the sensory system. And we'll talk about the pathway of that in a few minutes. And then we have, towards the back here, and a little bit in the front, though we aren't going to discuss the front part as much, we have the pyramidal tracts. Pyramidal tracts, also known as the cortical spinal tracts. And since they're in red and they're coming from the brain, they are all what? Sensory or motor? Motor. They all have to be motor. So everything in blue is sensory going up. Everything in red is motor coming down. All right. So that's how we get to and from the brain. But how do we get out to the periphery? All right. So we have the anterior horn here and the posterior horn here of the gray matter of the spinal cord. Which one receives sensory information? Posterior. Posterior receives sensory. So that means motor comes out through the anterior. All right? So that would be motor tract coming out, sensory tract coming in. These would be rootlets. So we have the sensory rootlet or dorsal rootlet and the ventral rootlet. Here would be the spinal root. All right, so the rootlets come out, form the spinal root, which is both sensory and motor. And then you go out to the anterior posterior. Okay, the anterior, God, I'm missing the word for it. This is why I make notes and remind myself. Rami. So posterior rami, anterior rami. Posterior goes to the skin of the back and the muscles of the back. The anterior rami go to everything else. Okay, just to remind you of that pathway. All right, now we'll get into a little bit of the function. All right. I don't know if anybody's ever gone over this with you, but some guy named Brodmann went through painstaking detail over years, decades actually, to slice up brains and look at the cytoarchitecture. In other words, look at the cells within the brain. And what he noticed is that the cell structure is different in different parts of the brain. And he mapped all of that. He didn't map anything, his graduate students did. So, mapped all of that, and we call those Brodmann areas. Brodmann areas just represent the difference in cellular structure. Now, years later, I think this was done in the 40s and 50s. Years later, we know the function of some of these areas, and what do we know? The function of these areas map to the discrete areas that Brodmann mapped, right? So if you notice here, for this area right here, what would you say that is? No. That would be the motor cortex. And then 1 and 2 here, going down on the backside, would be your somatosensory cortex. So he really provided the physical basis for the functions that we now know of the brain. So that's what we're going to try to do, is look at the functions of the brain, because we know that these spots are different cellularly. All right? We know the central sulcus. We know that this is the primary motor cortex, and this is the primary sensory cortex. Just anterior to that, that would be your supplementary motor, right? Supplementary motor, which is basically taking the motor information and doing fine-tuning it. And then back here would be your somatosensory association area, basically taking sensory information and integrating it together, because you notice that this sensory integration area is coming from the temporal lobe, which is involved in what? Hearing. The occipital lobe, which is involved in vision, and integrating them. Okay? And then we have this part here that's associated with elaboration of thought or thinking. What do we call that area? We named it already. Prefrontal cortex. All right? So now we're just providing functions to those different areas that we've already talked about. So, if you have a stroke in your prefrontal cortex, how's that going to manifest? This is where you need to go with this. Pardon? Right. How would it manifest? If you had a stroke and you destroyed the prefrontal cortex, could you remember anything? No. So, amnesia, long-term amnesia, retrograde amnesia. What about the ability to form new thoughts or form new long-term memories? With that, you couldn't do that either. What would happen if you had a stroke that destroyed the temporal area, the temporal lobe? Could you hear? You can hear. Absolutely. You didn't destroy the ear. You destroyed your ability to process that auditory information. So imagine everything coming in being nonsensical. You don't know what's going on. You hear noises, but they don't make sense to you. Okay? What would happen if you just had a stroke that destroyed the occipital region?
I'm gonna be able to process what you're saying.
You can't process visual information. There's a condition where this actually happens, where people's eyes work perfectly fine, but you move things in their vision and they can't detect that. So they're cognitively blind, but not physically blind. It's a weird phenomenon. So think about those things when you're going through some of your disorders in your subsequent ClidMed lectures. We talked about this, the prefrontal association area, limbic association area. Okay, so our ability to translate emotions into something that's more societally appropriate, socially appropriate. Thank you. I don't know who I'm saying thank you to. You ever heard of somebody? There's a couple movies, and I don't remember what they are, based on this. Dysfunction in their temporal lobe, like they have a temporal lobe problem, and they're psychopaths, right? So if you have problems with your temporal lobe, that's associated with psychopathic behavior as well, due to the fact that it's within the limbic association area. So not just hearing. And then you have your parietal occipital temporal association area, which is integrating vision, hearing, sensory information from the somatosensory cortex. That's what allows you to, if I see right in front of Nick here, a big steaming pile of dog poop, and I see it and I smell it, I know that when I stick my finger in it, what it's going to feel like. I know that's a really bad example, but it gets the point home, right? Because you've had experience with that before. You see it, you smell it, you're integrating all those things so that you know what's going to happen if you stick your finger in it. And you know for the next few days you're not going to be able to get that smell off your finger. All right. So, a couple more areas. Right here in the motor area, connected to the auditory area, that's called broca's. That is your sensory speech or motor speech? Motor speech. All right. So if you have problems in that area, you have problems. You know what you want to say, but you can't quite get it out the right way. Wernicke's area then, over here in the sensory region, you have trouble comprehending language. Not just verbal language, but written language as well. All right, so language comprehension. So language comprehension there. All right, and then just a reminder of the sensory motor areas. Remember, we have this little homunculus. Lower body is within the medial portion of the brain. Then as you go out, you go to the upper body, to the face, lips, tongue, and so on. So out and to the side, lower body to upper body. Same thing with sensory, lower body to upper body. That's how it's organized. Now we're going to use this in a little bit coming up. Briefly, function of cerebellum. We already talked a little bit about this. We have the fovea and the fissures within them. General functions, proprioception. I walk around the room, I don't fall down and break my face open. It's because of my cerebellum. Equilibrium, vestibular function. That means that your cerebellum is also connected to your what? Inner ear. Your inner ear, right? Muscle tone, coordination, motor learning, all of that occurs in the cerebellum. So if you have cerebellar dysfunction, and when you guys do your neuro exam in physical exam lab, there are certain tests you do for this, and they're all going to involve what? Gross motor skills and balance. We also know that our cerebellum, think motor, cerebellum is motor. Think of it as that little motor that's on a moped, like. It's connected to the midbrain, it's connected to the pons, and it's connected to the medulla oblongata. All right, so it has connections to all those areas. What do we know about the midbrain? The superior and inferior colliculi. Superior colliculi are associated with what? What other sense? Vision. Vision, thank you. And the inferior colliculi are associated with, what did you say? Hearing. Good. Are connected with hearing. So that means vision and hearing are associated with motor function. All right, and this slide just says that. All right, your corpora quadrigemina, which we saw in the MRIs, visual pathways, auditory pathways. Okay? Pons, general function, we know it's involved in the respiratory system, but it also connects to the cerebellum, so there are some cerebellar motor functions associated with the pons as well. And then the medulla, primary regulation of autonomic functions, respiratory, cardiovascular, we know that. But it also is involved specific areas, the olives on either side of the pyramids. So these are the pyramids, these are the olives. Olives are involved in motor coordination as well. And the pyramids are involved in your cortical spinal tract. What happens in the pyramids to your cortical spinal tract? The crossover. What's that term we use for crossing over? It's a decussate, right? They decussate. Actually, it's right here, decussation of pyramids. All right, reminder about the cranial nerves. How many are there? 12. Olfactory, optic, come on, say them with me. Oculomotor, trochlear, trigeminal, abducens, facial. Finally, vestibulocochlear, vested, German, glossopharyngeal, viewed, vagus, accessory, hop, hypoglossal. That's how I remember it. All right, so they are numbered front to back. Now, what your IOs want you to remember is that some of them are associated with parts of the brainstem. All right, so which are associated with the brainstem? The midbrain, cranial nerve 4. And I have them kind of labeled out here, what they're associated with. So these little letters are what that is. So the midbrain pons junction, that's cranial nerve 3, so it sits between the midbrain and the pons. The pons itself is associated with cranial nerve 5, the pons medulla junction 6, 7, 8, and the medulla itself 9 through 12. Okay, so most of your cranial nerves are associated with the brainstem, specific parts that they're coming out of, and they come out of very specific nuclei within the brainstem. Okay, the two that aren't are our olfactory and our optic. Okay, so those are the only two that are not associated with the brainstem. Everything else is. Now, it's going to come up in a couple of your, I was going to say pre-med, clin-med lectures, bulbar problems or bulbar palsies. Those have to do with your bulbar nerves. Your bulbar nerves are 9, 10, 11, and 12. Glossopharyngeal, vagus, accessory, hypoglossal. What's common with all of those in terms of origin? Where's their origin? The medulla. The medulla used to be called the bulb because it sticks out. Not like the pons does, but it is a bulb, a bulge in the spinal cord. So that's where they got their name. But they also have a common function. Glossopharyngeal. Vagus, which we know is associated with digestive activities. Accessory, which is involved with some of our back and neck muscles, but also with some pharynx and larynx areas. And the hypoglossal, which is involved with the tongue. So all of these, common function would be this area right here. Right? So if you have bulbar palsies, what would you expect to be affected? Swallowing, eating, things like that. All right. Officially, cortical spinal tract. Remember, if in the name, look at the name. The first part of the name is where the nerve starts. The second part of the name is where it's going to. So cortical spinal means it's starting in the cortex, the brain, and it's going to the spinal cord. So that means it's going up or down? Down, and that means it's sensory or motor? Motor. So the cortical spinal tract is a descending motor tract. Right? It's also known as the pyramidal tract. Why? Because it decussates in the pyramid. All right, the majority of the fibers, in fact, the ones you really need to be concerned about, end up in the lateral portion of the spinal cord, the lateral cortical spinal tract. Some of them end up in the anterior. We're not as concerned about those. Okay, so we're going to focus on the lateral cortical spinal tract, which is your arms and legs. All right, just to show you kind of the complexity of this, here are sensory neurons coming into the spinal cord. They always come in posterior. So here's posterior, anterior. Some of them, if you follow, are directly synapsed with the motor neuron. When a sensory neuron is directly synapsed with the motor neuron and comes out, you have a cause and effect. What do we call that? Begins with R, rhymes with heclex. Reflex. Okay, so that would be reflex. So what the hell are all these other things? What are they doing? First of all, what are all these type of neurons right here within the gray matter? What are those called? Interneurons. What do interneurons do? They serve as intermediaries between sensory and motor, right? So notice that these interneurons are connected to areas coming from the cortical spinal tract, coming from the cerebrospinal tract, reticulospinal tract. If you want to know the functions of cerebrospinal tract, they're in the notes of these slides. I put them there for you guys, as well as for myself. So I won't cover that. They can influence or be influenced by sensory neurons coming in. Okay? So they will come and directly synapse onto a motor neuron, but they also interact with interneurons to modulate the effects of the motor pathway. All right, so that's what this slide is intended to show you. What we're talking about with the cortical spinal, this yellow is corticospinal, coming here. It goes to an interneuron, goes to another interneuron, goes to another interneuron, and then synapses onto the motor. So we talk about the corticospinal tract coming down and then going out another motor neuron, but are they directly connected? No. So that means that some other stuff is happening within there to control what this motor nerve is going to do based on the information it's receiving from the corticospinal tract. So, since we're talking about motor neurons, let's define what the difference between an upper motor neuron and a lower motor neuron is, because they're going to have different signs and symptoms depending on which is affected. So an upper motor neuron is that which is coming from the cortex. What would this be controlling? I put the homunculus here. What do you think would be controlled right here? Leg? What about here? Probably arm. Okay? So you notice the leg is coming down. Coming down, coming down, coming down, coming down, coming down. Oh, it's going to the lumbar region. That makes sense, right? Arm. Coming down, coming down, coming down. Crosses over. Arm. In this cervical region. That makes sense. So that's where these pathways are going. If there is a from here to from this part of the cortex down to the cervical region, that would be that upper motor neuron. From this area down to the lumbar region, where it synapses, that would be the upper motor neuron for the leg. All right, so the upper motor neuron is completely contained within the central nervous system. All right, so if you have a upper motor neuron problem, you probably have a problem with your brain or your starts with an S, rhymes with spinal cord. Okay, so that's upper motor neurons. All right, another thing to notice. Where do not notice, but remember, upper motor neurons cross over, and where do they cross over? The pyramids of the medulla. So they go to the medulla, cross over, then head down. That's going to be important for a discussion later on. So then what are lower motor neurons? Lower motor neurons are coming from the gray matter, out the anterior, and out to their appropriate limb. All right, so this one, since it's in the cervical region, this would go to our arm. This one down here would go to leg. So a lower motor neuron is primarily associated with the periphery. So upper motor neuron is within the central nervous system. Lower motor neuron is not. All right, remember there are two types. We have alpha motor neurons, which are the ones that are going to be causing the contractions. Like when we say corticospinal, go down and contract. It's going to be the alpha motor neurons that do that. Gamma motor neurons are involved in generating tension and reflexes. Okay, we're not going to get into the details of that. So, what happens when we have an upper motor neuron lesion? All right, I want you to think about this. Upper motor neuron lesion could happen in the brain, central nervous system. Could happen here in the medulla, central nervous system. Could happen here in the cervical or lumbar region. Okay? As long as it's happening in the central nervous system, it's going to be an upper motor neuron disease because it affects the upper motor neuron. All right. So, if we destroy, let's, for argument's sake, say we destroy this part in the medulla. Okay? car accident. All right? What are we going to see? Well, what have we destroyed? What connection have we destroyed? The brain to the lower motor neuron. Okay, we've destroyed the connection between the brain and the lower motor neuron. But have we destroyed the connection from the central nervous system to the muscle? No. So we still have a cord going from the central nervous system to the muscle, but we've destroyed the connection coming from the brain. Okay? So, do we still have input going to the muscle? Yes, that's important. With upper motor neurons, the lower motor neuron is still intact. So you're still having output that can go to the muscle. What does that mean? As far as muscle mass, if we can't think about it and control my arm contracting, it's not going to contract very much. Right? So we're going to, if we don't use muscles, what happened to them? They atrophy, right? So we have some atrophy from disuse. As far as strength goes, we're going to have what's called spastic paralysis. And spastic paralysis doesn't mean this. It means tense muscles. I can't move my muscles, but they're tense. Like I can't move, but I still have a contraction going on. Right? That's what spastic paralysis is. Why do we have spastic paralysis? Because we still have that lower motor neuron that's sending signals. Okay? And where are those signals coming from? What's still intact here? I lost conscious control, but what's still intact? Begins with R, rhymes with key flex. Reflexes. So our reflex pathways are still intact. So that's going to keep our muscles in a tense position. The tone, muscle tone, hypertonia. What does that mean? I'm still going to be able to feel a contraction. If I go and feel Nick's muscle, he has hypertonia, I'm still going to be able to feel that muscle being contracted as opposed to just flap, right? Reflexes, you're going to have hyperreflexia. Why? Because it's those reflexes that are still intact, not the conscious control. Remember, what did we do when we took the hammer and we hit the knee and did the knee jerk reflex? How did we get that to go even farther? Gender stick maneuver. What did that do? That took out conscious control. Therefore, we kicked harder. So this lesion took out conscious control. We're going to have hyperreflexes. Does that make sense? You're not going to have fasciculations. We'll talk about what those are in a minute. But you will see a positive Babinski sign. All right? Do you guys know what the Babinski sign is? You take your hammer, the pointy end, the metal part, and you stroke it up the foot. What you're supposed to happen in an adult is this. If you have an upper motor neuron lesion, you're going to see this. Right? So it's supposed to be like this. You're supposed to flex, but they will splay out. Okay? Lower motor neuron lesions. All right. I can still consciously think and send a signal down to my spinal cord. But because my lower motor neuron coming out is affected, I'm not going to be able to get that signal to the muscle. Right? So I still have the central signal coming down, but I have no connection to the muscle at all whatsoever. So I can't send any signals to the muscle, not even reflexes. Okay? That's important because if you can't send reflex signals, are you going to have that tone you had with upper motor neurons? No. So you're going to have significant atrophy. You can't use that muscle. You can't use those muscles at all. So you're just going to be limp, completely limp. That's going to lead to a flaccid paralysis. So again, I go to Nick, I feel his arm. It's just going to feel flabby. Nothing's going to be there. no tone whatsoever because I have no signals going to it. So hypotonia, hyporeflexia because those reflex pathways are gone. You won't see a Babinski sign. That makes sense. And you'll see fasciculations. And it might be hard to see it here in this video. In fact, you can't see them at all. Oh, there we go. Do you see those little, almost looks like bugs or worms crawling in this leg? Why is that happening? For the same reason like why you get eye twitches or why you get, these random muscle twitches here, because the muscle, electrolyte problems are causing the muscle to do things it's not supposed to do. All right, so I'm going to skip by this just in the interest of time. I know we're over. I'm sorry. I always go over, right? But these are examples of upper and lower motor neuron diseases. Do you guys want to take a break? Or are you just going as you please?
We have to eat lunch before that.
Yeah, go. I need to eat lunch too.
Are we coming back and you're leaving or what? Because we should just finish. Yeah. Or are we just done?
What do you guys want to do? It's up to you. How many slides do you have left? 16. Do you want me to do a recording? And I'll just record it for you? Or do you want to go through? Okay, we'll finish now. I'll do it quick. All right, reminder about sensory tracts. All right, we have the dorsal column, medial limb distal, which is associated with touch, vibration, and position. Hand, foot, cervical lumbar. Remember, it goes in, goes up to the medulla, crosses over, and then to the part of the brain. So touch and position, like where you are in space, up to the medulla, cross over, then go to the appropriate parts of the brain. Pain and temperature, foot, hand, lumbar, cervical, cross at the level of where they come in and then go up. Right? So pain and temperature, touch and vibration go up opposite sides of the cord from each other. Okay? That's important to remember. So when we have spinal cord lesions such as Brown-Séquard syndrome, which you can get from trauma or tumors, what happens is this. And this is why I brought out my colored markers. Let's look at motor. This would be right side, left side. Okay? Here's your cortex. Motor's going to come down, cross over in the medulla, right? Head down to the arm and go out. Okay? So starting the left side, coming down the right side. Touch. Touch is going in. Is it going to cross over or travel up? No. It's going to travel up and then cross over in the medulla. Pain and temperature, what's it going to do? Go in, cross over, and then go up. Okay? So, if I have a lesion in my spinal cord on one side, let's say the right side, on the right side, what have I lost? touch or position, no movement, but I still have pain and temperature. Okay? On the left side, I have touch, I have movement, but I have no temperature. So it's a weird phenomenon, and it has to do with the fact that pain and temperature cross over at the level of input where the others cross over in the medulla. Does that make sense? Okay. So, if you missed that drawing, I have it all right here. Same drawings right there. Okay, so the next slide would be the same drawings that I just put there. Yeah. So, what we don't have, what we do have. All right, anterior cord syndrome. If you have like your anterior spinal artery, you have ischemia, the front part of the spinal cord dies. So that means you're losing your anterolateral system and your anterior corticospinal tracts. You're going to have motor paralysis below the level of the lesion. So motor paralysis below the level of the lesion. Loss of pain and temperature at and below the level of the lesion. Wait a minute. Yeah. But your touch, position, and vibration will be intact. Because touch, position, and vibration are coming from here. The back part. So that's why those are still going to be intact. Posterior cord syndrome. I've taken out the dorsal column, median meniscal. So what's going to be affected below the level? Loss of touch, position, and vibration. All right, think about what these different areas of the spinal cord do, and if you get rid of them. Motor function is going to be intact because I still have our motor pathways. And pain and temperature are going to be intact because they come from up in the front as well. So front part of the spinal cord, loss of one thing, back part of the spinal cord, loss of another. Central cord syndrome. If I have problems with the central cord, it's smushing things. That's our scientific term, it's smushing. All right? These are things that could happen. It could happen from. We're going to have descending gradient of weakness. So arms are going to be weaker than the legs. Why is that? Because all of the this is white matter. Your arms are first, then it goes down the body. So if you're smashing the nerves that are associated with the arms, but less smashing with the legs, your arms are going to be weaker than your legs. Does that make sense? So you're pushing outwards. The inside is going to be more smushed than the outside, so that's going to be the primary thing that's affected as far as motor goes. With sensory impairment, it's going to be mixed. It could be all over the place. And you're going to have bladder dysfunction. In other words, you can't pee, so you're going to have retention of urine. And then this one makes sense. If you have a spinal cord transection, like I just cut through the spinal cord, what's going to happen below the level of the lesion? You're going to have nothing, zero, no motor, no sensory. You got rid of everything, so that makes sense. But it depends on the location, right? If it happens down here, let's say at the umbilicus, I've gotten rid of leg function. If it happens in the cervical region, I've gotten rid of arm and leg function. All right? Remind yourself of dermatomes and brachial plexus. The last thing I want to cover, spinal nerve abnormalities. All right, 3 terms you need to be familiar with. They are slightly different but sound the same. A radiculopathy. ridiculous. Okay? One or more nerve roots are not functioning properly, so it's a pinched nerve. Right? Radiculopath, radiculopath, a pinched nerve. So one nerve is affected. Sciatic nerve, sciatica is an example of this. So one nerve is affected. That's a radiculopath. It's ridiculous that only one is affected. A plexopathy would affect a plexus. Where do we have plexuses? Brachial plexus, lumbar plexus, sacral plexus. So if you have a plexopathy, how many nerves are affected? One? Multiple. You're affecting the whole network of nerves. All right? So that would be affecting your brachial lumosacral plexus. If you have peripheral neuropathy, that would be affecting just a lower motor neuron. Okay, a lower motor neuron out in the periphery. You wouldn't be affecting the whole neuron, just where it innervates. Okay? So if you have diabetic foot neuropathy, you're just affecting the nerves that go to an area of the foot. Does that make sense? So that's the difference between these terms. So if you see them come up, it's ridiculous that only one nerve is affected because you could have the whole plexus affected, or you could just have diabetic neuropathy. And then neuromuscular junction disorders. Remind yourself that motor neurons go to the neuromuscular junction and release acetylcholine. Okay? So if you have a problem with this process, anything that affects you opening neuron channels in the muscle, what's going to happen is progressive muscle weakness. So it's not going to happen all at once. It's going to occur over a long period of time. And it's going to start with smaller muscles, like in the eye, in the mouth, and the throat, the bulbar muscles. And then it's going to progress. All right? Generally speaking, if it's a neuromuscular junction disorder, are you going to have sensory involvement? No, you shouldn't, because it's just at the neuromuscular junction. Does the autonomic nervous system go to muscles? No, so you shouldn't have any autonomic involvement, so it shouldn't affect digestion, for example, and no GI involvement, which is what I just said. Okay? Reflexes are going to be completely normal. Okay? Examples of this, myasthenia gravis, which is an autoimmune disease, botulism toxicity, that's another example. All right, I am sorry for taking so long. We'll leave it there.
I would. Hold on.